Hello and welcome to the second part of our lecture where we're talking about heterostructures, and on this part we're going to talk about the double heterostructure. We'll start by considering a double heterostructure which itself consists of two heterojunctions. So one heterojunction between a heavily doped p-type aluminum gallium arsenide material and a lightly doped p-type gallium arsenide material. So this is illustrated right here. You have on the left here the blue and the green material corresponding to the heavily doped p-type aluminum gallium arsenide, and the lightly doped p-type gallium arsenide, which is a different material altogether, which has a smaller band gap than the aluminum gallium arsenide. And also notice that since this guy right here is heavily doped p-type material, the Fermi level is going to be much closer to the valence band than this guy, which is also a p-type material. But since it's lightly doped, the Fermi level is slightly below the halfway position between the conduction and the valence band, so it's just a little bit down towards the valence band. Okay, but then there's the other junction, which is a junction between the p-type gallium arsenide, this material here, and an n-type heavily doped aluminum gallium arsenide material, right? So on the same device here you have another junction between this middle material here and the material on the right. Now the material in the middle here we've seen is a p-type gallium arsenide, which is lightly doped. On the right here we have again heavily doped n-type aluminum gallium arsenide material. Okay, so it's different because it's n-type, but it's also heavily doped, and this means that the Fermi level, since it's n-type material, is up towards the conduction band. And because it's heavily doped, this means that the Fermi level is very close to the band edge for the conduction band. Okay, so again, the gallium arsenide, which is lightly doped, has a smaller band gap, as we've seen, and is sandwiched between the two aluminum gallium arsenide materials, the heavily doped P and N type aluminum gallium arsenides on either extremity. You have right here in the middle the lightly doped gallium arsenide, which has a smaller gap, right, than the aluminum gallium arsenide on either side. This illustrates the band diagram before physical contact. What does this mean? We're looking at the isolated band diagrams of the three materials here, right, before you even build a device and allow for carriers to move around. So there, it's like this heavily doped p-type material is isolated from the center material, and the same thing happens between these two materials here. Now let's examine what happens when the junctions are brought into physical contact. So when this happens, there is a difference in carrier concentration on either side of both junctions, right? What does this mean? Well, this means that there are way more electrons on the n-type material, right, in the conduction band than there are in the p-type gallium arsenide material. So electrons, when this is brought into physical contact, electrons will flow, from here into the p-type gallium arsenide, and both the heavily doped p-type aluminum gallium arsenide and the lightly doped p-type gallium arsenide are p-type materials, but the heavily doped aluminum gallium arsenide has a much larger hole concentration. So since there are more holes here, we expect that holes will tend to diffuse into this material right here. So you have flow, and also the minority carriers will also tend to diffuse as well, right? So thinking about the holes here, you have more holes in this p-type material than you have in this n-type material. So we have holes diffusing in the opposite direction here as well. But we have also to take into account that this will happen to a much smaller degree, though it will happen, because you have the potential barrier here, right? So the holes need to overcome this potential barrier, the electrons here need to overcome this potential barrier, but there will be a flow of carriers down here and up here as well. And also we'll have depletion layers forming, right? So because of this diffusion of electrons and holes which will recombine, you'll have positive immobile ions on this side and negative immobile ions on this side, just like we have seen in a heterojunction and a simple homojunction before. So all of these things will happen as well here. Now the majority carriers inside the heavily doped p-type aluminum gallium arsenide, as well as in the p-type gallium arsenide, are holes, and the majority carriers inside the n-type heavily doped aluminum gallium arsenide material are electrons. And since there are more electrons in the heavily doped n-type aluminum gallium arsenide, which is the material on the right, there's a flow of electrons towards the left, as we've seen, so towards the middle gallium arsenide material. So this is the flow that we've illustrated right here. But what will this cause? Well, after contact, the heavily doped n-type aluminum gallium arsenide material will be at a higher electrostatic potential V, because, you know, if electrons have diffused to the left here, this has left this material at a larger electrostatic potential, at a larger V. But we've seen that the potential energy will actually be smaller. So since the electrostatic potential V is larger, the potential energy, which is just the charge of the electrons times V, will be smaller, or will be more negative, right? And therefore this material will have a smaller potential energy. So this whole band will move down with respect to the one in the center right here, right, until the Fermi levels align. So this will move down until this Fermi level aligns with this one right here. Okay, and since there are more holes in the heavily doped p-type aluminum gallium arsenide, which is the material on the left, there's a flow of these carriers towards the center material, as we've seen, and after contact, the center material will be at a higher potential and a lower potential energy than the heavily doped p-type aluminum gallium arsenide layer. So again, because of this flow of holes which are positive charged, the green material here will be at a higher electrostatic potential V, and therefore will be at a smaller potential energy. So again, this material right here, the band diagram of this material will move down with respect to the band diagram of the material on the left, and this will happen until this Fermi level aligns with this one right here. Okay, does this make sense? The Fermi levels will align. The whole band diagram of the n-type material, which is at a higher electrostatic potential and therefore lower potential energy, will move down with respect to this, to the band diagram of the center material right here. The same thing will happen to the center material here, because holes have moved here. It is at a larger electrostatic potential V, but this means a lower potential energy, so this whole band diagram here has moved down. In the junctions, the bands have bent, right, with the S shape that we've seen before, and also considering the potential barriers that were there originally, they're still there. Now notice that in all of the junctions you have the S-shape bending of the bands, so looking like this, right? The you know, the upside down parabola and the right side up parabola. In all of these junctions, this is the behavior, but the discontinuity that is there, or the potential barrier, is still the same, right? It's still right at the center here of the bending. So if this discontinuity goes down, like in this case right here, then you'll have, you know, the same thing when the bending occurs. So you know, if you have the first part, which is the upside down parabola, then you have the discontinuity which is going down, then you have the right side up parabola right here. On the other hand, if the discontinuity goes up, right, I'm talking about when you look, you know, from left to right, and in this case this discontinuity here is going up, or in the original diagram, you know, this discontinuity here is going up from left to right, whereas this discontinuity is going down from left to right. Well, when it goes up, it will still go up once the bend. So what will happen then is that, you know, you'll have the first part, which is the upside down parabola. Then, because it goes up, you know, the discontinuity or the potential barrier goes up, then it'll go up here, and then you have the second part, you know, the right side up parabola here. So you have something like this, right? So this illustrates the two cases that can happen, but in this way you can, you know, kind of draw or construct the bending that happens. Another important consideration is that electrons flowing from the heavily doped N-type material into the center P-type material are trapped in this layer, in the center material, due to the potential barriers at the first junction, the one on the left, right? So you know, the electrons that have moved here, because this is an N-type material, so there will be a flow of electrons, they can't go up because this is now a much larger potential barrier than this was, right? So the electrons will have a difficult time moving up here, and fewer electrons will be able to overcome this barrier, and therefore these electrons will be effectively trapped in the conduction band of the center material right here, right? Because they cannot, you know, overcome this barrier. Also, holes flowing from the heavily doped P-type material to the left into the center material are trapped in this center material as well, due to the potential barrier for holes at the second junction. So, which potential barrier I'm talking about here? This one, right? The holes have moved right, or have diffused from this heavily doped material, because there are excess of holes here, so they will diffuse, and there will be a diffusion current to the right, diffusion current consisting of holes moving to the right, but these holes will have a hard time overcoming this barrier here, right? Because again, it's a much larger barrier, so you effectively in the valence band of the center material, the middle material, the P-type gallium arsenide, in the valence band there will be a lot of holes, and in the conduction band a lot of electrons. So this is the beauty of the double heterostructure. You're able to confine a lot of carriers to a very small region, which you can make as small as you are able to, considering fabrication limitations, but which can be made very small. So therefore you're able to confine both types of carriers to a very small region, which is a single region in space. Okay, so the middle region, which is also called the active region, or the active layer, is able to confine carriers of both types, electrons and holes. Now, what happens when you forward bias, when you apply a forward potential to the double heterostructure? So by applying a positive voltage, which means that you apply a voltage source in such a way that the P-type material, or the heavily doped p-type aluminum gallium arsenide material is at a larger potential than the n-type material, right? So again, you will apply an external potential in this way right here to bias it directly, right? So this will be a more positive potential than the n-type material, and this potential difference will bring the heavily doped n-type material side to a lower electric potential, which translates into a higher potential energy. Okay, now what are we saying here? So this is the junction without any bias, without any external voltage source applied, right? Because of the flow of carriers, the bands will bend, and this is the new band diagram for the device. But once you apply a positive bias here, like we've illustrated, this will change again, right? And since you're applying an electrostatic potential, which will make the potential of the N plus side lower, more negative, this will translate to a larger potential energy. So this positive, this direct bias here will bring the band diagram of this N-type material up, because it will go up in potential energy since it's at a lower electrostatic potential, right? And the same thing will happen to the center material right here. It will move up once you apply this external, direct bias right here. It will move up for the same reason, right? Because the leftmost material here is now at a higher electrostatic potential, and therefore it will be at a smaller or at a lower potential energy. So this will bring this band diagram down with respect to the center one, which is the same thing as saying that the band diagram of the center region here will move up. Okay, so the band diagrams will bend again, right? The heavily doped N-type material will move up in energy, as we've just said, and it will actually now look like this. So this is with the external, direct bias, which we've just discussed. So you're applying positive potential to the p-type material on the left, and this will bring, again, as we've discussed, the whole band diagram of the N-type material up with respect to the center material, and the whole band diagram of the center material up with respect to the heavily doped p-type aluminum gallium arsenide, and the bands will now look like this, right? The Fermi levels have split, so you have two Fermi levels, one for the left and one for the right here, but the band bending will now become less prominent, as is illustrated here. So you still have the upside down and the right side up parabola, but since this guy has moved up in energy and this guy has moved up in energy, it becomes smaller. So this bending has become smaller, and well, due to the applied electric field, there is an additional flow of holes towards the right and electrons towards the left. So what does this mean? Since you have an applied electrostatic potential, which will cause a voltage drop here, there will be an electric field from left to right, from the more positive potential to the more negative potential. You'll have an electric field in this direction here, which will cause further holes, to move in this way, and electrons to move in that way. Okay, so this external potential will make more electrons flow from the heavily doped N-type material into the center region here, And another way to think of this, you know, it has to make sense with the electric field, but another way to make sense of this is that now the potential barriers have decreased, right? This barrier here, this barrier right here, which is seen by the electrons in the heavily doped N-type material here, is much smaller than this barrier here. Okay, and this happened because of the external applied field. So more electrons will be able to move here. And the same thing happens here for holes, right? This potential barrier here for holes is smaller than this one right here. Okay, so consistent with what we said, right? The holes will move along the electric field direction. You have a movement of holes here because this potential barrier is smaller. Okay, so as you apply a direct bias, a positive direct bias, you know, you polarize the junction, the structure in such a way that the p-type material is at a higher electrostatic potential, you'll be causing more electrons to flow to diffuse into the active layer, and more holes to diffuse into this active layer. So the carrier concentration for electrons in holes in this active region right here will be even larger when you apply a direct or positive bias, as we've illustrated. And this is important because in order to build lasers and LEDs, you know, all these types of light sources, you need lots of electrons and lots of holes in the same region, because the recombination of these electrons and holes is going to cause the emission of light. And if you have a very large concentration of electrons and holes in the same region, you'll have effective light emitters in this way. So this is the nice thing about the double heterostructure, which was a Nobel Prize, I think, from the year 2000. So you can look this up, but that's the idea behind this device. Okay, guys, so thanks a lot for your attention, and I'll see you on our next lecture.